Now we'll talk about electrochemical impedance spectroscopy, or EIS. EIS is one of the electrochemical methods that we can use to understand battery materials and their properties. EIS can give us information about electrolyte resistance, bulk materials resistance, and grain boundary resistance. Coupled with galvanostatic cycling with potential limitations, or GCPL, we can understand a battery's capacity and hysteresis. Coupled with galvanostatic intermittent titration technique, or GIT, we can understand the diffusion coefficients of ions within the material. First, we'll discuss electrochemical impedance spectroscopy using an analogy. Similar to UV-vis spectroscopy, in which the input is light at a certain wavelength, we can measure the output signal and understand how much of the signal has been transmitted. And we can gain information about the effective frequency on the sample. In EIS, we can measure impedance upon applied alternating current, which will give us information about the total flow of electrons. And the change in amplitude and phase are related to the impedance. We can model resistance and capacitances using simple circuit components to analyze output signal from EIS. The signals represent physical phenomena with different timescales. The physical processes that we'd like to understand are electrolyte resistance, charge transfer resistance, interfacial charge separation, double layer capacitance, grain boundary resistance, grain boundary capacitance, diffusion of ions in the electrolytes, distribution of the properties due to non-uniformity of the materials, and diffusion coefficients. For the case of lithium-ion batteries, once the circuit is closed and we have turned on the battery, there will be a migration of charge species at the electrode interface. This forms a double layer of charges, and chemical compounds at this interface will begin to reduce and oxidize in the electrochemical cell. DC measurements will reach steady state conditions pretty quickly, so we need to use AC to separate timescales of different phenomena in the battery material. And here's an example of an equivalent circuit that can model these processes. AC impedance contains real and imaginary components. The magnitude of impedance and the phase difference between the input voltage and output current can be correlated with physical phenomena that we're trying to probe in the materials. The real component, or resistance, impedes current by dissipating energy, and the imaginary part, or reactance, impedes current by storing the energy. We can use resistors to model electrolyte resistance and charge transfer resistance. The resistor circuit component has zero phase lag from the input voltage to output current signal. And the data can be plotted along the x-axis. Capacitors can be used to model interfacial charge separation, double layer capacitance, and grain boundary capacitance. Impedance of capacitors is related by 1 over I times the frequency times capacitance. The phase lag is negative 90 degrees between voltage and output current. We can see here that the data is plotted along the y-axis from high frequency to low frequency. Constant phase element is similar to capacitance and allows us to model real electrodes. Typically, they're porous with non-uniform boundaries and contain materials with distribution of particle sizes such as deviation from ideality, and will yield fitted alpha component exponent between 0 and 1. The Warburg impedance models diffusion in electrolytes. This non-ideal diffusion is a special case of constant phase element, and it subsumes non-idealities of real electrode. Nyquist plot, as seen here, of processes that occur in the same location as the battery can be modeled with circuit elements in parallel. The characteristic frequency of such process can be determined from the Nyquist plot. For example, double-layer capacitance that occurs at the electrode-electrolyte interface can be modeled with a capacitor. Oxidation or reduction of the electrode can be modeled as a resistor. At high frequency, or large value of omega, impedance is small and the current goes through the capacitor. At low frequency or small value of omega, impedance is estimated to be R. The Randles circuit is a popular equivalent circuit for modeling semi-infinite diffusion-controlled Faradaic reactions in planar electrodes. The Faradaic reaction is controlled by diffusion of reactants to the electrode surface. The Warburg diffusion is in series with the charge transfer resistance, and the diffusion coefficient of lithium ions can be calculated based on the known molar volume active material, Faraday's constant, the area of the electrode, the open circuit potential of the known composition of lithium in the active material, and the slope of the measured real or imaginary component of impedance versus inverse square root of frequency.